This is video number 93 in our series on tensor calculus. In this video, we're going to introduce the geodesic curvature tensor. This is an object that will be very useful in analyzing curves that are embedded in surfaces. In the last video, we introduced this normal to the curve. We said that because a curve embedded in a plane can be treated as a hypersurface, this new object is entirely analogous to the surface normal we developed earlier. What we want to do now is to explore its properties in more detail. So let's start by recalling what we know about the surface normal. First of all, the normal does not lie on the tangent plane. And because of that, we have to use ambient indexes and coordinates to represent the normal. So we represent our normal as a linear combination using the ambient vector component contracted with the ambient basis vector in either one of these two forms. Well, likewise, since this normal does not lie on the curve over here, we can't use the curve coordinate to represent it. We have to use the surface coordinates. So in a form analogous to this, we'd say that our new object n hat here is going to be represented as a linear combination of n alpha using surface coordinates now times the surface basis vector s alpha, and of course it can be represented this way too, n alpha in the lower position with a contravariant basis vector. Now in video number 63 we derived explicit formulas for these normal components. You'll remember these forms that we derived back in video 63. Well, we could go through the same analysis and derive similar expressions for this new normal right over here, but we don't have to do that. We've already done the work here. All we have to do is to adapt these forms for this situation over here. And what I mean by adapt is we have to reduce these forms to one less dimension. And you'll remember anytime we're dealing with these Levi-Civita symbols and so on, we have to make some adjustments anytime the number of dimensions changes. So let's work on that just a minute. So if we're going to come up with a formula for n alpha, the normal component here, we're going to do it in one less dimension, which means instead of the ambient indexes, we're going to need surface indexes. So instead of ni, we'll have n alpha. Well, secondly here, this factor of 1 over 2 factorial in 2 dimensions instead of 3 is going to reduce to 1 over 1 factorial. And then the first factor here, this Levi-Civita symbol, over here it's got ambient indexes. We need surface indexes, but also these Levi-Civita symbols require that the number of indexes match the dimension. So not only do they need to be surface indexes, but they need to be only 2 of them to match the degree. So here we're going to have alpha and beta only. Likewise, this Levi-Civita symbol that has 2 indexes in it here is only going to have 1, and it's going to be the curve index down here. So this will be phi and only 1 index. And finally, we have 2 shift tensor factors over here. In this form, we only need 1. This number of factors has to equal the number of dimensions. So this is going to be a surface shift tensor, and it's only going to be 1, and it's going to have the index of phi and beta. So there's the expression for n alpha in the upper position. And of course we can duplicate this by flip-flopping the indexes to get the expression for n alpha with alpha in the lower position. Now you'll recall that there are 2 very important properties of our surface normal. First of all, it's a unit vector. That means that n hat dotted with itself is going to be equal to 1. And secondly, it's orthogonal to our surface basis vector. So n hat dotted with s alpha is going to give us a value of 0. We represent both of those properties in vector component form with these relationships. This is the equivalent of the dot product with n hat with itself, and that gives us a value of 1. This is the equivalent of the dot product of n hat with the surface basis vector S alpha. That gives us a value of 0. Well, the same properties exist for this new object that we've defined over here. We'll find that n alpha contracted with n alpha, like this, will give us a value of 1, and n alpha contracted with the surface shift tensor S alpha phi, like this, will give us a value of 0. And that tells us that we have a unit vector and that this vector is orthogonal to the curve at the point of evaluation. Now, these are properties that you can easily validate for yourself simply by direct substitution of the expressions we have up here. Okay, all this ties together and makes perfect sense for a curve embedded in a plane. But what happens when we're dealing with a surface that's curved? Well, the definition here and all of these properties are the same and work equally well there. However, I do need to point out an important difference in the geometric interpretation. In the case of a plane, we noted that n hat here is the exact equivalent of the principal normal p hat that we derived back in video 76. However, this is not going to be the case for curved surfaces. Now, both p hat and n hat are unit vectors, and both are orthogonal to the curve, but while n hat here lies in the tangent plane, p hat lies in the plane of the curvature. Now, these two planes are different and only coincide when the surface is a plane. Thus, the two objects in general point in different directions. It's only when the surface is a plane that they're going to point in the same direction. You'll see that more clearly in a few minutes. So let's move on with the analysis. Let's look again at this chain relationship that we discovered in the last video. What we're going to do now is to multiply both sides by the covariant basis vector zi. From video 60, we recognize this contraction as the equivalent of our surface covariant basis vector S alpha. Likewise, from video 88, we recognize this contraction as the equivalent of our curve covariant basis vector U phi. So that means that we can rewrite our expression this way. Next, we'll take the covariant derivative of both sides, and of course that means on the right-hand side we're going to have to use the product rule. From video 89, we recognize the left-hand side of this equation as simply the definition for our vector curvature normal. So the left side of our equation here is going to be equal to our vector quantity b with the indexes phi and psi. This is just our vector curvature normal. Now let's pick on this term right here. What we've got is a covariant derivative with respect to a curve index of an object that has a surface index. And this being the case, we can expand this out using the chain rule for the covariant derivative. In other words, this expression right here is the equivalent of S beta psi times the covariant derivative with respect to beta of our object S alpha. So this again is just the chain rule for the covariant derivative. This expression right here is the exact equivalent of this one. But of course, here you should recognize this part of the expression as our definition for the surface curvature tensor. And we'll find that discussion back in video number 71. So we can rewrite this expression this way. Our shift tensor S beta psi times this expression, which is nothing more than the surface curvature tensor B alpha beta times the surface normal n hat. All right, so with all of this, we can now replace this second term with these factors plus this additional shift tensor. So we'll write it in this order. We'll start with the surface normal right here, n hat, and then our curvature tensor, B alpha beta, and that followed by our two shift tensor factors. We'll use this one first, S alpha phi, and then this one S beta psi. At this point, we want to introduce a new definition. We're going to say that the covariant derivative with respect to psi of shift tensor S alpha phi is going to be equal to a new object represented with a lowercase b, index is phi and psi, times the normal component that we introduced earlier in the video. So what we're defining here is this new object b phi psi, and we're going to call it the geodesic curvature tensor. Now you'll notice that the free indexes here match up on both sides of the equation, as of course they should. But if this is going to be a valid definition, there's something else we need to do. You'll remember we said that our new normal here is perpendicular to the curve. And we demonstrated that by showing that the contraction between a shift tensor such as S sigma alpha with this component is going to be equal to 0. This is just the vector component method of finding the dot product between our normal and the curve covariant basis vector. Well, if this is going to be a valid definition, we have to show that the same property exists for the left-hand side. In other words, if we take this object over here and we contract it with the shift tensor S sigma alpha, we have to demonstrate that this expression is also equal to 0. Otherwise, this definition doesn't make any sense. So let's go over and demonstrate that this property is true. What we'll do is to expand our expression out using the rules of the covariant derivative. So this is going to be, first of all, equal to the partial derivative, as always. We start with the partial derivative of our object, S alpha phi, with respect to u psi. And then I'm going to need two terms with Christoffel symbols, one for each of these two indexes. Now the first index is in the upper position, so that means it's a positive term. And the upper index is a surface index, and we're taking the derivative with respect to a curve index, so we're going to need this form. We need a shift tensor times the Christoffel symbol. We're going to need a dummy index right here. And the lower index here matches this one, which is psi. The upper index is going to remain alpha. And finally, we need to form a contraction with our object. We'll use omega as the dummy index. The lower index is phi. Okay, that takes care of the alpha index. And the second index is the lower index, so we need a negative term. It is a curve index, so we just need a curve Christoffel symbol. And the indexes here would be psi and phi. And the upper index is going to be a dummy index as we form the contraction here, and the upper index is going to remain alpha like that. So this is the full expansion of the covariant derivative of this object. So what we'll do now is to multiply through by S sigma alpha. So all I've done here, other than rearrange the terms a little bit, is to multiply it through by this term on both sides of the expression. Okay, now if you go back to video number 90, you'll recall this expression that we derived for the conversion of the Christoffel symbol from surface coordinates to curve coordinates. Well, by renaming these indexes a little bit, you can see that the pattern here is that these two terms together will give us the Christoffel symbol for sigma psi phi. All right. Now, on this side over here in this term, we've got a contraction going on right here on the long index. And anytime that happens, remember, the result of the combination of these two shift tensors contracting along the long index will give us a delta factor, in this case delta sigma delta, and this delta factor will absorb the delta index, and over here we're going to get a term of negative gamma sigma psi and phi. That's because this index is absorbed right here and it becomes sigma. Well, obviously this term equals the negative this, and so the whole thing then is equal to 0. And that's what we set out to prove. This expression right here is equal to 0. And that in turn means that this term right here is orthogonal to the curve. And that's what we set out to prove. All right, so now that we know that this expression is true, we rightly conclude that this is a reasonable definition for our new object, the geodesic curvature tensor. Okay, well, while we're here, let me point out one other thing, and that is that our new object here is a second-rank symmetric tensor. This expression is symmetric with respect to these two indexes. Well, how do we know that? Well, we can show it this way. Let's copy this expression, renaming phi and psi as well as alpha and beta. Okay, well, we know that our vector curvature normal is symmetric with respect to its indexes, so these two expressions are exactly the same. And we know because these indexes are symmetric and the order of these terms doesn't matter, these commute, that this expression is equal to this one. And therefore, if this equals this and this equals this, then it has to be true that this term equals this one. And that demonstrates what we're trying to prove here, that this expression is symmetric with respect to phi and psi. So these two indexes are symmetric. With this new definition, we can now rewrite this expression up here this way. So all I've done here is to replace this term with this as per our new definition. Okay, well, the next thing is I want to do a little index juggling. I want to raise the psi index into the upper position and form a contraction. And of course, to do that, we would multiply through by the contravariant metric tensor and then rename the index. But by now, you should be able to see how that works by inspection. So we're going to, first of all, raise this index into the upper position and rename it to phi. We'll do the same thing over here, and we'll do the same thing over here. And while we're at it, we're also going to lower the beta index here and raise it in this position. Remember, we can always flip-flop the position of a dummy index. And finally, notice that this factor combined with this one is the equivalent of our vector n hat. This is just the linear combination that represents our new normal vector right here. So applying all of these changes, we can now write the expression this way. Now, by doing this, we have now formed a full contraction. Every one of the indexes in this expression is a dummy index, and therefore it's a full contraction, which means, of course, that we have an invariant expression. Well, we're almost done, but there is one more thing I want to do. You'll notice that there is a contraction between these two shift tensor factors. Now, if that contraction occurred on the long index, on the surface indexes here, then we'd simply see the result to be a delta function right here. But the contraction is on the short index. You'll remember that means something totally different. You go back to video 66, you'll remember that discussion. And in video 66, you'll remember this identity. We said the normal projection operator added to the surface projection operator will yield this delta function right here. So we can reorder the terms here to make it look like this. What this tells us is that the contraction of our shift tensors along the short index will yield the delta function minus the product of the normal components here. So what we need to do is to adapt this result to two dimensions. And so to do that, it would look this way. It would be S alpha phi times s phi beta, and that would be equal to our delta function here with indexes alpha and beta, and this product right here would be with our new normal in alpha and beta. So this expression right up here is the equivalent of this. So what we can do now is to expand this term out this way. We'll have b beta alpha times this expression instead of this one. So it's delta alpha beta minus the product of our normal components in alpha and beta. So let's expand this out. This term times this one will result in the absorption of the beta index. So this times this factor is just going to give us b alpha alpha, and then of course the second term, b beta alpha times n alpha and beta. And finally we can flip-flop the beta index here, and this becomes b alpha alpha minus b alpha beta times n alpha and beta. So what we can do now is to replace this expression right here with this, and that'll give us the final expression that we're looking for. Well, after all of that, what do we have here? Notice there are three curvature tensors in play in this equation. We have this one, the vector curvature normal, and that quantifies the curvature of our curve as it relates to the ambient space. Well, then we have this curvature tensor, which quantifies the curvature of the surface that's embedded in the ambient space. And finally, we have this guy, the new one, the geodesic curvature tensor, which quantifies the curvature of our curve as it relates to the surface. So this equation relates these three curvature tensors with one another. Now, notice that this vector right here, of course, points in the direction of the surface normal. And this term over here is perpendicular to it. Remember, this new normal right here lies in the tangent plane of the surface, and therefore it's perpendicular to the surface normal. So what we have here is a vector that could point in any direction that has been decomposed into its normal projection and its surface projection. And that gives us the opportunity to analyze these components independently of each other. And that's exactly what we're going to do in the next few videos. Okay, well, one final observation here. We know that our vector curvature normal is perpendicular to the curve. We also know that this new normal here is perpendicular to the curve. And since all three of these vectors must lie in the same plane, that means that this vector is also perpendicular to the curve. And in particular, that tells us that the surface normal is perpendicular to our curve, as well as each of these other two vectors. Okay, so with that, let's take a break and go over and do a quick recap of what we've accomplished in this video. The first thing we did was to define this new normal. It's analogous to the surface normal in hat that we developed back in video 63. It's defined by three properties. First of all, it's a unit vector. Secondly, it is perpendicular to the curve. And finally, it lies in the tangent plane of the surface. Now, because it lies in the tangent plane, it can be represented as a linear combination using our surface basis vectors like this. We also developed these explicit formulas for the vector components of this normal. These expressions are similar in form to those of the components for the surface normal, again referring back to video number 63. Next, we defined a new object called the Geodesic Curvature Tensor, this object right here. Now we showed that this is a reasonable definition by demonstrating that, like n alpha here, this expression on the left-hand side is always perpendicular to the curve. Now, I've also included here an explicit expression for this new object, which we obtain by simply contracting both sides of this expression within alpha. When we do this, this product right here becomes 1, and that isolates this object on one side of the equation. Finally, we made use of these new objects to derive this expression. Now what this does is to decompose our vector curvature normal into its normal projection and its surface projection. Remember that little n hat here lies in the tangent plane, so n hat is perpendicular to the surface normal right here. So this allows us to analyze these components separately. Now note also that the surface normal, little n hat here, and the vector curvature normal are all perpendicular to the curve. They lie in the same plane that is perpendicular to the curve itself. Now, this result clearly demonstrates the geometric meaning of the geodesic curvature tensor. Because n hat is a unit vector, then this factor is obviously the magnitude of the surface projection. And that's the meaning of the geodesic curvature tensor. Now, note for a plane surface that the plane curvature tensor, this guy right here, vanishes. It's equal to 0, and this whole term drops out of the expression. And in that special case, the vector curvature normal is the exact equivalent of this term over here. So when we're talking about a plane surface, n hat here is the exact equivalent of our principal normal p hat, and our geodesic curvature tensor is the equivalent of the curvature kappa of the curve itself. Okay, well in the next video I'm going to demonstrate these concepts with a specific example.